And now it is my very great pleasure to introduce tonight's special panel discussion. As we conclude our 25th anniversary celebrations this year, we're so pleased to celebrate the 100th anniversary of quantum mechanics. This has been the focus of a conference taking place at Perimeter this week, 100 Years of Quantum, Perspectives on its Past, Present, and Future, bringing together researchers to discuss the history, philosophy, and physics of quantum mechanics. The panel discussion taking place tonight features esteemed speakers from this week's event. Tonight's panelists include Dr. Benjamin Schumacher from Kenyon College, Dr. Elise Kroll from the City University of New York, Dr. Jas Uffink from the University of Minnesota, and Dr. Matthew Leifer from Chapman University. The panel will be expertly moderated by Dr. Adam Becker, journalist, author, and astrophysicist. And I will hand it off to him to kick things off tonight. So please join me in welcoming Dr. Becker and our esteemed panel.
Thank you. So let's get started. It has been 100 years since Werner Heisenberg and his colleagues wrote down the first real theory of quantum mechanics. And we've been celebrating it all week and all year. So I'm going to start by giving the four of you an infuriatingly simple question. What is quantum theory? Matt, why don't you start?
Okay. If I say anything wrong, then the other panelists will correct me. So it's good to be in the first place.
But it will go on your scorecard.
So quantum physics started as the subject of studying very small things like atoms, electrons, and subatomic particles and things like that. But as far as we know it today, it is the framework of quantum physics is one of the two most fundamental frameworks of physical theories that we have. So as far as we know, everything is quantum mechanical in some sense or another. The effects are most pronounced at the atomic level, but in principle, the whole world is quantum mechanics.
Elise? Yeah. It looked like you wanted to respond.
Oh, did it?
Yeah.
Okay. Make sure not to make that face again.
Oh.
Just kidding. So at the end of the 1800s and early 1900s, we still didn't have a really good theory of how light and matter interact. And some of the physicists struggling with this ended up coming up with a theory that departed from theories that were classical, that describes their everyday things, chairs, tables, how footballs fly through the air, things like that. Football is a game we play in the US, sorry. But it had really strange, unexpected properties, and so it's even more interesting that now we consider quantum theory to be possibly able to describe everything that there is in the physical world, because it still has these maybe interesting properties that are unexpected and unintuitive in certain ways.
Well, I was going to say more or less the same thing, that by the end of the 19th century, there was a perfectly good classical theory of light, and there was a perfectly good classical theory of matter. But on every occasion where light is either emitted or absorbed by matter, strange things happened. Matter, atoms could only absorb or emit light at very peculiar frequencies. And nobody at the time understood why that was or how that is. And there were many other puzzles like that. There was a photoelectric effect, also discovered in 1880 or 1890, I'm not quite sure now. And then Max Planck and later Einstein posited this hypothesis that maybe light is a sort of corpuscle that contains an energy packet of a given size. And that idea evolved in the course of time, especially in the hands of Bohr with his first model of the atom, into the idea that even the atom could only exist in certain particular states of energy, which it could change by absorbing one of these packets or emitting one of these packets. And that, in turn, led to a whole theory of the entire periodic table of all the chemical elements. It was extraordinarily successful, but it was also extraordinarily mysterious at the time. How could it be that atoms could only absorb or emit these particular energy quanta, as they became known? And that took 15 years in which dozens or more people tried to break their heads on how to make sense of all this. And then in 25, when Heisenberg was alone on the island, he said, all of these people have been trying to build pictures about what goes on inside the atom. And he said, all of a sudden, let's throw that all out of the window. Let's not make pictures anymore. Let's just focus on the things that we can actually observe about the atom, which is not how the electrons move around inside. We shouldn't try to build pictures of what goes on there. We should just concentrate on these very few observable quantities. And he built an extraordinarily abstract theory to deal with that. But it was also extraordinarily successful, and that's how quantum mechanics came to be. It was extremely successful, but at the same time, it was also extremely mysterious in comparison to the classical theories before.
Well, the people like Heisenberg and the others who came up with quantum theory, they had to give up a lot. They had to give up a lot of intuitions, a lot of preconceptions, as you were saying. They had to give up the notion that particles have trajectories through space. They had to give up the notion that two particles, that if I had a very definite state of two particles, that entailed that either particle had a definite state. There were just all kinds of really strange things that took a long time and still take a long time for people to get their minds around. And it is a very striking thing about quantum mechanics that it is 100 years old, and there is still a lively discussion, a lively debate about how we should understand it and how we should interpret it. That is a remarkable thing. I can't think of anything else quite so impenetrable and therefore wonderful.
And why do you think that's happening? Like, why has it lasted 100 years like that? Why has this debate gone on for so long?
Okay, so I have a theory.
Okay. Yeah.
There's a certain sense in which the really distinctive features of quantum mechanics emerge when the system is not being observed. So quantum mechanics is what happens when nobody is looking. Okay? And that means that the kinds of questions we ask ourselves, like, what is it like to be an electron in an atom,
Yeah.
turn out not to actually have any content, because we can't. The electron is isolated from us, is informationally isolated from us, and so I think that because that's so unlike our everyday experience, it's just hard to give up those habits of thought.
I mean, think about it. If you're a scientist, or anyone, I guess, who's trying to build a brand new theory to explain hitherto unexplained phenomena, what are you going to do? Can you really invent something from scratch, or do you have to use previously well-established theories to sort of guide your reasoning? And you see this interplay. Of course, as people the size that we are, as creatures the size we are, and that we engage with things in the world that are what philosophers call medium-sized dry goods. We developed first in our history as a human species theories of physics that could explain the behaviors and states of medium-sized dry goods, right? And we built theories to be intuitive, to make sense of the pictures we had of the world. In the development of quantum theory to address some of these phenomena we could not address, classical theories broke down. And so even though today in quantum theory we use terms like momentum and position and superpositions and all this, these classical terms are only kind of approximately describing what's really going on. And so there's a mystery, and there's a question of whether we will ever be able to have intuitions about the quantum world because of just how we evolved to be as a species. It's gonna be unintuitive, but how creative can we get to sort of get beyond our intuitions? Yeah.
Great.
Can I make a response to that? Yeah. I mean, I think I don't really buy the idea that it's because, this is a theory about objects that are of a different size, because we don't really have the same kinds of questions about the cosmic scale, right? So we didn't evolve to think about galaxies and the Big Bang and things like that. But we don't seem to have the same kind of conceptual problems with general relativity. There are some problems with it. But
we don't have a quantized theory of gravity yet. That's kind of a big problem.
That is true. But I think theories are built by humans, and if we don't have intuitions about them, it's because we didn't found them in a way that was conducive to have intuitions. It's not necessarily the world's fault, right?
Oh, I didn't mean to blame the world. I'm sorry.
Okay, so you're saying that it has something to do with the way that theory was initially devised.
Yeah, I would say that. So most physical theories prior to quantum mechanics start with an idea of what it is that they're trying to explain, right? So in classical mechanics, you have particles, they have trajectories, maybe you have fields. So, when these ideas are introduced, it's sort of clear what they are and what they're supposed to do. Quantum mechanics was introduced with clear ideas as well, but the trouble is it was introduced with at least two sets of different clear ideas, which then had to be sort of munged together to make a theory work. So you had the original matrix mechanics, which is what we're celebrating the anniversary of, developed by Heisenberg and then Born and Jordan. And, it's kind of started from the idea that you have states of definite energy, and from time to time, they just jump from one state to another. And that's sort of the picture that you have. Probability is in there right from the beginning. And then you have the sort of Schrödinger point of view where everything's one giant wave function. There's a giant wave that describes everything. Schrödinger initially wanted to think of that as a wave evolving in space, but that didn't work out. And eventually they had to import the idea of probability from the other side, right? But, both sides have ideas that come from the other, which don't really, although we have unified the mathematical framework of these theories and now it's one thing, it's not one set of conceptual ideas. And I think one of the reasons why people have very different intuitions, even physicists have very different intuitions about what quantum mechanics is about, is because it does have these different starting points, and people are confused about what's most fundamental.
Yeah. Good. Okay. So, Elise, I'm going to pick on you a little bit. Yeah. No, it's okay. So, at the core of these interpretational debates, right, that have been going on for a century, is something called the measurement problem. Now, I'm not going to make you try to solve the measurement problem here on stage like other people have done, but I am going to ask if you can tell us what the measurement problem is.
Well, I think the measurement problem is a group of problems, but
Okay.
I'll state one version of the measurement problem that I think many of the interpretations latch onto. So as Matt was saying, there's a probabilistic element to this theory. Namely, we have a law that evolves deterministically, But nevertheless, when we do a measurement, the best we can do beforehand is give a probability spread saying, oh, it's more or less likely to be, the system is more or less likely to be found in this state and not the other. But when we do a measurement, we don't see, well, first of all, we don't see a probability spread. We see a definite outcome. We see a value, a ping on the screen, right up where the Geiger counter goes bing or whatever. And so how do we get from a probabilistic theory to a specific outcome? There must be another story to be told there. And also because in quantum mechanics, you can have states that are superpositions. I mentioned that before. And when we think about normally wavy stuff, ripples in a pond or something, if you drop a stone in and I drop a stone in, the waves can, superimpose, right? And you can get really big peaks and really small troughs. And this is perfectly normal for wavy type stuff, but one of the things that was realized with experiments in the early 1910s and 20s is that both light and matter can behave as both particles and waves. And so there's a sense in which this wavy description of the world should also describe macroscopic systems. So Adam, you could be, according to quantum mechanics, in a superposition of here and there. But we don't see you in a superposition of here and there unless our context lenses are, a little blurry or something. So how do we explain the fact that these states are allowed states? There are ways that quantum systems can be and probably should most of the time be. But yet we don't see things in superpositions most of the time. We see them sitting in one well-defined place or pinging in one spot on the screen. So that's one way of thinking about the measurement problem. Yeah.
Anybody else want to add to that?
Yeah, here's another way to think of the measurement problem. Elisa is completely right. I mean, so Heisenberg started it off by not using any pictures at all. But then Schrödinger came along and he supported, but very particularly, the idea that actually atoms are sort of, or electrons or everything in the universe is actually some kind of wave. He was sort of thinking originally as a sort of cloud charge that was oscillating. But as Matt has also pointed out, his view didn't last very long because it actually had internal problems of its own. And so on the other side, there were people who were promoting more or less this particle view. And yes, there were lots of experiments where electrons or other systems behaved like particles, even atoms, of course. But then there were other experiments, as you said, in which they behaved like waves. And so after 25, and certainly in the 27 and 8 and all the way in the 30s, people were trying to break their head on, well, what are they really? Are they really waves or are they really particles? They couldn't just try to reconcile all of that. And it was actually Niels Bohr, who was Heisenberg's mentor, who finally sort of found a solution. And his solution was, he said, it depends on the measurement you perform, the kind of experiment in which you study these systems. In some experiments, they behave like waves. And in other experiments, they behave like particles. And so you could ask, but are they then particles and waves? No, because it turned out those experiments cannot be performed simultaneously. They exclude each other. So in some experiments, you need a wave picture. And in other experiments, you need a particle picture. But you never need them both at the same time. And Bohr was happy with this, and this became the sort of orthodox view on quantum mechanics. And it's only at the time Einstein was not happy with that view. But it's because it's a peculiar solution that Bohr proposed. Because now, and now I'm coming to the measurement problem, because it depends on the type of measurement you perform, what picture of reality is applicable. And so it's not like you had in classical physics where you said, oh, this is what reality is like, this is what our theory tells us. And now we're going to study what kind of experiments we're going to perform. No, you first have to decide what the experiment is, the measurement. And then you can tell a concrete story about what's going on. And so the measurement plays a very peculiar role in deciding what picture of reality you should employ. And this is something so unlike any classical theory that, and that leads to the question, well, if you look further, what actually is an experiment? What is a measurement? I mean, isn't a measurement just some peculiar type of physical interaction with ordinary physical systems that we should be trying to decide by physical theory? No, in this view, it has to be an experimenter who decides to perform something. And that's why the observer plays an important role in quantum mechanics.
Okay, but what's an observer?
Yeah, well, it's something that stands outside of the theory. It's us, and of course Einstein wasn't the only one who objected to the view. It's closely connected to this measurement problem is a thought experiment that Schrödinger proposed a few years later. And it's a kind of cruel experiment because he says, but he didn't do it in actual practice, but he said, just suppose you put a cat in a steel chamber and together with a bottle of poison and some mechanism that could break the bottle of poison connected to a radioactive atom. And the radioactive atom is surely described by quantum mechanics. And so as long as we don't observe it, it could be in this superposition of not being decayed and decaying. And if it decays, it will trigger this mechanism that breaks the hammer and kills the cat. But if it does not decay, then the bottle would be intact, the cat would be alive, and everything, all of this is enclosed in this steel chamber. And so Schrödinger devised this baroque example just to show that, well, if you follow Bohr and his interpretation of quantum mechanics, then you're forced to the conclusion that as long as you haven't looked inside the box, the cat is neither dead or alive because you can't really apply any particular picture of reality. But as soon as somebody opens the box, performs a measurement, then it will be decided whether the atom has decayed, whether the cat is alive or the cat is dead. So it seems like there's only an outcome once the measurement is performed. And as long as we don't perform a measurement, there are no outcomes. There's no definite reality at all. And, well, Schrödinger just presented this example to show how weird the consequences of Bohr's view actually were.
It's the consequences of his own equation, though. So it wasn't just Bohr's view.
It was Bohr's view
and
on his equation.
So Einstein had first written a letter to Schrödinger saying, look, I get that you like your wave function. I get that you like your equation. It's great. It does all these things for you, but it cannot describe reality because if I apply it to a description of something macroscopic, like a pile of gunpowder, then it tells me that after a year or something, if that pile of gunpowder is suitably unstable, I should mathematically describe it, according to your quantum theory, as being in some weird mixture of exploded and not exploded. But in
Yeah.
reality, there's just no such thing as a middle ground between exploded and unexploded.
That's-
So your description, your mathematical formalism doesn't describe what we really see. And Schrödinger responds and said, yeah, I've got a cat. But
No. Schrödinger responded, I have given up that interpretation of my wave function
Yes, that's
years ago.
we still don't have a good interpretation of the wave function. So.
Yeah.
I just wanted to say what my view on what the problem is. So the measurement problem is a funny problem because we've solved it about 5 or 6 times differently, unfortunately. And so part of the problem is to just know what it really was that we were looking for at the end of the day. So when I look at the history of foundations and interpretations of quantum mechanics, I see it primarily as a problem of quantum jumps. Okay, so Schrödinger talked about the problem of quantum jumps, but I'm talking about the modern problem of quantum jumps, which is that quantum physicists are always jumping to conclusions. And basically what we've had to do over the years is sort of uncover what are the implicit assumptions that people are making, and how can we really investigate the full space of possible realities that underlie these theories. So when I look at some of these older debates that were going on in the early days of quantum theory, it feels a bit shocking the extent to which the evidence on which they were prepared to sort of throw out the existence of an objective reality to some degree. We have actually much better evidence for that now, but I think the history of the subject has been over time to make less and less of those implicit assumptions, and that's probably why it's taken 100 years.
And did you have any?
Well, I think the measurement problem is just one subspecies of a much broader problem, which is how does the macroscopic world, which does not have all these properties that quantum systems have, apparently, how does and we use the term classical for that. How does the classical world emerge from quantum mechanics? I mean, presumably, the objects we see here and the apparatus in my laboratory and me, we're all made of atoms, right? The atoms are quantum mechanical. So how is it that this quantum mechanical thing that's going on leads to this very different appearance of the world? And the measurement problem is just a way of saying that, but it's really much more general.
Yep, good. So, Matt, like you were saying, this is something that we've solved several times at least. And generally, these solutions are called interpretations, right? Broadly, right? And so there are many different interpretations of quantum mechanics. There's the many worlds interpretation. There's pilot waves. There are many options. How do you all feel about the different options on the table for interpreting quantum theory and solving the measurement problem? Hughes, I'll start with you.
Me?
Yeah.
Okay. Well, I've been asked that question many times because I taught a course on the interpretation of quantum mechanics in Minneapolis, and very often students would come to me and say, well, what is your favorite interpretation? Do you prefer this pilot wave or the Broglie-Bohm theory, or do you prefer the Everett interpretation, or what else we have, the Girardi-Rimini-Weber approach, and
That's a collapse picture.
the collapse interpretation, yeah, and so there were several others that we discussed during the course, and I invariably said in the end that I believe in the law of conservation of misery. And that's just to say that each of these interpretations has very nice features. They solve something or other. But it's like a waterbed, right? You push down on one side, and then the problem comes up somewhere else.
And you lose a lot of sleep in the meantime.
Yeah. So each of those interpretations has nice features, but then they also have consequences that you have to pay for those nice features. And so in the pilot wave theory, there's non-locality of a very mysterious kind that doesn't decrease with distance. In the many worlds interpretation of Everett, you have to multiply the universe billions and gazillions of times, and they're not observable in any way. There's all these different universes, and you can't possibly have any contact with them. And that's kind of bizarre. And so on. I mean, I don't have a favorite interpretation. I think there are all possible ways to try and understand this strange theory that we have of quantum theory. And in a sense, the fact that there are all these different approaches and that none of them are perfectly nice shows us what a acute problem this is and what a difficult problem it is.
Yeah. Ben?
Well, I've tried very hard not to officially sign on to any interpretational school of quantum mechanics because I think the more positive way of saying what Jos was saying is that I think all of them have some advantages and suggest some interesting questions to answer. So I think that, for instance, the many worlds interpretation, I think it has problems. On the other hand, it suggests a lot of really interesting calculations to do, a lot of interesting questions to ask, which can lead you to new things. I think probably by temperament, I favor, what's the phrase that's been used in our meeting? A Copenhagen-ish interpretation. Copenhagen interpretation, of course, is the kind of interpretation championed by Bohr and his collaborators, including to some extent Heisenberg, though we can. The philosophers will have a much better idea of the distinctions here. But the quantum theory, as we understand it now, does sort of require this. Quantum mechanics is kind of the bottom-up description, but it requires, in order to be even well-defined, a sort of top-down cosmic classical theory, and that in order to make sense. And so maybe you can think of quantum mechanics of arbitrarily large systems, but just not everything. And so that's my instinct. But of course, when I say that, it sounds terrible and really fuzzy and doesn't seem to work at all. And I say, you really believe that? And so I can't really say that I do. So that's where I am.
Well, also, speaking as someone trained as a cosmologist, I want to be able to use quantum mechanics to describe everything.
Mm-hmm.
Yeah. Elise?
So you all are like a bunch of politicians up here, not answering the question. Allow me to be blunt. Controversy. I think there are no solutions because we're asking a classical question of a non-classical theory. Wow. What it is to ask how we go from a system that is still sort of only to be described probabilistically from what appears to be, according to our macroscopic measuring devices, effectively definite, is to ask for a mechanistic or a causal story that takes us from A to B, and that is just not what quantum theory tells us the way the world is. If you don't like that, here's another point. of these interpretations, we're pretty sure that the best theory is going to be a relativistic theory. And the only one of these interpretations that has a somewhat persuasive relativistic version is the Everettians. So they're not even necessarily playing on the same field. But you're right, the Everettians have this massive story about what is real, and it includes like many versions of myself. That is a lot of metaphysics that I do not want to inherit. But yeah, this more pragmatic questions, like these theories, these solutions are still having to do with non-relativistic quantum mechanics, and we know that's not the final story. But then maybe the reason we don't agree on the interpretation is because it's the wrong question.
Very possible.
What?
I said very possible.
Yeah.
That is the wrong question.
I don't agree here.
The philosopher speaks.
You excuse me of being too politically correct, but I think every physical theory, every serious physical theory, deserves an interpretation.
Sure.
And that's just what we ask of quantum mechanics. You can say, well, you're looking, your intuition is that you're looking for a causal or mechanistic story. I don't think that's right. I mean, this is something that has often been said to Einstein and his colleagues who were critical of quantum mechanics. Oh, you just want to go back to the old classical theory. No, that's not true. It's especially true in the case of the work of John Bell, because you don't presuppose that reality has to be something that we're familiar with in classical physics, like a story of billiard ball type molecules bouncing around. No, reality could be anything. It could be composed of things that we haven't even thought of. It could be fields that we haven't thought. Things that require a kind of mathematics that we haven't even thought of. It could be bizarre, but the only requirement is there is something definite about it. There is a picture that you can paint of that.
Is that not an assumption that?
Oh, it's an assumption, but it's not necessarily causal. It's not necessarily mechanistic. It's just the idea that there is something independent that, and Einstein puts this very well in his autobiographical notes. He said what he objects to in quantum mechanics is that it deviates from something which has always been the goal of physics, that it should provide you with a picture of physical reality independent of an observer and what choices that observer makes. And that's, as I just said, is not what Bohr gives you. Bohr gives you the view, first tell me which experiment the observer is doing, and then I will give you a picture of reality. And Einstein says, no, you first have to have a picture of reality, and only then shall we talk about what experiments we can do. But that picture of reality has to be independent of the observer. That's the only requirement that he puts on his desired goal of interpreting quantum mechanics.
Okay, I'm gonna just give.
And so
we can talk offline about it.
Yeah. Okay. Again, the debate is alive and well.
Yeah.
We just wanted to give the people a real-time example of what's going on. Yeah.
Matt.
So on the question of interpretation, again, I also taught this subject, and the students at the end tend to say, yeah, so which one is the right one? My answer to that is always none of the above. There's something a bit fishy about all of these options. However, I think a more important thing to say is that I just reject this premise that there's something called an interpretation of quantum mechanics. It's a very bizarre idea. So in classical mechanics, when you're teaching it, you don't say, okay, here's some mathematics, and we're going to discuss that for a while. And then later on, we're going to discuss something called the interpretation of classical mechanics, which is about what it says is real. We do both of those things together. And it's really strange in quantum mechanics that we've separated these things. And I don't really think that most of the things that we call interpretations are merely interpretations. They're different physical theories which we haven't figured out how to separate yet. So, I mean, the path between an idea in physics and an actual experimental test can be very, very long. Not all ideas have obvious empirical content, but they might help us to develop ideas which directly do. So in particular, when we try to apply quantum mechanics in contexts where beyond its current realm of applicability, when we try to think about possible theories of quantum gravity, when we try to think about strange systems that, we expect that quantum mechanics will change somewhere. Some of the framework will change. And all of these ideas will start to make different predictions in that context because they give you different ideas about how to go at building the new theory. So as a physicist, my job, unfortunately, unlike the philosophers and historians, I can't just talk about what the current theory means. I have to hopefully try and build something new. And the reason I'm interested in this subject is that I think, I'm betting that thinking about these things more seriously will actually help us to build new physics and help us to separate these ideas eventually.
Great. Okay, so we're going to go to questions from the audience in just a minute, but before we do, I'm going to use my prerogative as moderator to ask one final question of all of you, but I'm going to ask you to keep your answers short so we can get to audience questions. I know, but as short as you can. So there's a lot of public interest in quantum physics, right? This is why everybody's here tonight. And I think that there's also a lot of, I think we're about to hear a lot of questions about quantum physics. And there's also a lot of misconceptions about quantum physics. And I thought about asking what's, the one misconception about quantum physics you wish would die, but I didn't want to end on such a downer. So instead, I'm going to ask a more positive version of the same question. What's something that you feel should be better known or you would like more people to know about quantum physics? And Ben, I'm going to start with you because I haven't given you a chance to go first yet.
Okay, so something that I wish was better known, better understood.
Yeah.
I think that this is going to sound so technical. I think the conditions under which we see these quantum effects. Yeah. That quantum effects are not things that you're not going to see wave interference in your dog. Okay, the conditions have to be pretty special because these quantum superpositions are very delicate, and so I think that might go some way to rationalizing people's understandings of what's going on.
No, I think that's a great answer. I don't think that's too technical. I think people know what dogs are.
Yeah. Schrodinger had a cat.
Yes. Your dog. Yeah. Who wants to go next?
Well, if you ask me which misconception I think I would like to remove from the general understanding,
sure, we can do
is that, I talked about Schrodinger's cat, and it's often, in the popular literature, you often read like the cat is both dead and alive at the same time. Or in other examples, people say, well, the electron can go through both slits at the same time. And people say about qubits that, they can be up and down at the same time. No, that's not what quantum mechanics says, because that would sound really mysterious. As I tried to say, there's one picture applicable in one situation, there's another picture in another experiment, and yet these two experiments exclude each other. And so, at least what in the orthodox version that Bohr proposed, you would simply say, dead and alive are just not applicable to the system as long as you haven't observed it. And after you have observed it, it's dead or it's alive. And before that, these notions simply don't apply. It's not that it's both dead and alive, it's neither. It's something unspeakable.
Elise?
I think, I disagree with you.
Aha!
Because, I mean, the technical, I'll give you a short technical, and I won't explain it, but I think the short technical answer, because I've encountered a lot of physicists that I still debate with about this, but would understand the role of decoherence in explaining certain classical to quantum transitions. But what we find in Nobel Prize winning physics experiments is that we can sophisticatedly build systems where we do see wave-like effects coming from bigger and bigger systems, and maybe a cat. Now, alive and dead is not really a basis in which we can do measurements, but we can exhibit systems, we can measure systems that Schrödinger kittens and so forth, right? Like very small, but compared to quanta, like massive, orders of magnitude bigger. But as a philosopher and a historian, the thing I'd like to correct is that what the popular books, yours excluded, of course, often pitch is that Einstein and Bohr and these guys had this debate. It was about being a realist or being an anti-realist and blah, blah, blah. We have really good historical evidence that shows not only that they just had these sort of crass debates about these, but that at the very start of developing quantum theory, everybody involved, even Schrödinger, these guys, understood that that interpretation was part of the physics itself. And so what I would say to Matt is not that you're right. When we're teaching classical mechanics, we don't say, here's the physics and then here's the interpretation. But what we take from that is not that quantum is special, but that every scientific theory requires interpretation. It just becomes very clear in the case of quantum physics. Every scientific theory requires interpretation.
Okay.
We agree.
By the way, I don't really disagree with that. I just think that
Now who's a politician?
the things that we've called interpretation in the case of quantum mechanics aren't interpretations.
That's fair.
Or they aren't mere interpretations, let's say that. But I'm going to choose something, I think, that is maybe a little bit of a technical analogy, but I wish more people understood it. Some of the things that we say about entanglement and stuff like that appear a bit contradictory to the popular audience, because we say entanglement's this really delicate thing that's hard to create. Oh, and by the way, things that interacting with each other and getting entangled all the time, and the entire universe is in this great big massive entangled state. And so people often, I think part of the reason why some people think that entanglement can have effects on the human scale is because, we tell them, like, all this stuff is happening. I think it would be helpful if people understood that entanglement is more like a secret than it is like another kind of a correlation. So let me tell you, right? So if I share a secret with everybody in this room, right? If I tell you, for example, I prefer DC Comics movies to Marvel Comics movies, that's a secret that I might not want you to share with the outside world. We all share that secret, and the reason it's a secret is because nobody outside this theater knows it, okay? But no pair of us shares a secret. If I pick a random member of the audience and say, do we share a secret? No, because everybody else knows about it. And so entanglement works like this, that the entire universe, all the particles in the universe together might be in some great big entangled state, but no pair of particles in the universe is in an entangled state, right? Because if you share a secret with everybody, then no subgroup shares a secret. So I think this is part of our understanding. This has to be part of our understanding of why the everyday world doesn't display these weird quantum effects. But that doesn't mean that there aren't classical analogies like this that we can use to understand them a bit better.
And with that, let's have a hand for our great panelists here.